Hello and welcome to the week 4 lecture series. In this week, we'll look at the PyTorch for accelerated training. In this lecture series, we will see the several aspects of training acceleration or how we can achieve the maximum speed while doing the AI training, AI workload training. This does not mean that we will also not talk about at all the inference. Obviously, part of the lecture will also focus on the inference part, but in broader sense, this series of lectures will see the accelerated training as the main goal or main focus. First, we will look at the tensors, definitions, autograd, what is exactly this mean, and also how it is implemented in the PyTorch and how it works. And also in the segment 2, we will see the model building with nn.module, which is the key package from the PyTorch framework. The training loops, we will in detail talk about training loop in the segment 3. In the segment 4, we will also talk about the data loader and data pipeline. This is going to be also very important from the training point of view, again because for the training we need the training data set to be loaded, and how we can make the better choice of data loader and data pipeline for the accelerated training that we will see. In the last segment, we will see different performance optimizations that can be applied to maximize the performance. Overall, we will cover the PyTorch based AI training and its acceleration. So, in segment 1, we will focus mostly on the PyTorch tensors, autograd and the computational graph. In the previous lectures, you have already seen the applications, how to implement or deploy the workflow in the containerized application and so on and so forth. So, you already know how to build models through PyTorch, but in this session we will also revisit few of the things that we may not have talked about, but in detail we will see how PyTorch is useful for defining the tensors and defining the autograd and basically the defining of computational graph, which is the key workflow of any AI training pipeline. So, by this end of this lecture, we will be learning how to create the tensors of any shape, the data type, the different arrangements, different shape, reshaping, slicing and reduction operations, broadcasting, different arithmetic operations that can be applied on the tensors. We will also explain the grad, right. So, gradient flow, how the gradient flows in the training pipeline, that also we will see through different calls, and also we will see from the practice point of view. Practically, we will see exactly how it works, how we can implement or deploy, or we can develop the workflows step by step. We will also distinguish between the leaf tensors, non-leaf tensors, detached tensors to understand the gradient flow, because these key tensors definitions will be required for you to understand how the gradient flows and which are the data it touches, which are the operation it touches for which it computes the gradient. So, starting with the PyTorch tensors. So, you all have seen this type of definitions, right. We can create the tensors through torch.tensor. So, from the data, like if we have the data, that then we can make sure that this data is provided here as a list, and basically from this we can make the tensors. So, tensors are nothing but the list in NumPy, the equivalent in the PyTorch, which is used in the AI workflow, usually the primitive data type, which is basically the tensors or the data structure, you can say. The torch.zeros will initialize the tensor with the 0.1s will initialize the tensor with 1s. The sizes will be defined by the arguments here, 3 by 4 matrix. Here you can see Here we are defining a 3-dimensional tensor with 2 by 3 by 4. So 2 by 3 by 4 tensor. So basically you can imagine that you have a 3 by 4 matrix which has 2 dimensions. Similarly, rand n, which is defining or initializing the torch with random values based on the matrix dimension or the tensor dimension that is defined in the arguments. We can arrange the torch from the data that is available. So 0 to 10 with the step of 2, you can see this will be initialized like this. Similarly, torch dot lines lean space or linear space. So basically this will be also evenly spaced values we can define or we can initialize as a tensors. So essentially the tensors are the data structure which is used, or the data that is used by the GPUs and basically defining through PyTorch framework here. Okay. The data types can be different data types. So torch.float32 will be by default, the model weights are defined by 4 bytes per element here, that is the 32-bit. Float 16 will or bfloat 16 will be half precision, which is 16 bits for GPU training. Mostly we use this which is of size 2 bytes or 16 bits. We have int4, so torch.int4 64 will be by default used by the integer tensor. So if we want integer tensors to be used, we usually use .int4 or int64 rather, and this is used for class labels, indices and so on and so forth, where these integers are required, right. So for weights and biases, mostly for the parameters, we do not usually use the int64 for the training obviously. For training we usually use the float 32 or float 16. We usually use float 16 or bfloat 16 based on the target. Torch.bool will be using boolean, or it makes the usually the mask out when we want to do for attention, like attention masking. We can use this true false. So torch.bool is another data type which is widely used for attention masking, let's say. Converting to the different data types. From one data type I can convert to different data types. Similarly, one example is x.2, then I can convert it to torch.float16, let's say, for an example. Similarly, we can use x.float, x.long, x.bool. Which data type I can convert, that we can give as the function. Device placement is also important. Where exactly my data should stay? We have defined the data as tensor, and the data type is also mentioned. In the practice session also we will see how to actually implement those, but we can define the data, we can define the data type, but where exactly we are keeping the data? Are we keeping inside the RAM of the CPU, or are we keeping inside the GPU RAM, right? Based on that, your GPU will be accessing or CPU will be accessing, and the speed will vary. So x equal to, let's say I am defining one tensor here, torch.rand n, which is random initialization for a 3 by 3 data. This usually lives in the CPU RAM. If we want to move to the GPU memory or GPU HBM, then we can use this 2.2 function, which is basically this method which will be argumented by the CUDA. So essentially if we have one single GPU, so then we can use CUDA. So it will take the data from CPU RAM to GPU RAM. So this is called the transfer of tensor from the GPU, CPU to GPU. Similarly, we can just also say x.CUDA, shorthand equivalent, and also we can use the CUDA colon the GPU number if we have multiple GPUs, GPU 0, GPU 1, GPU 2 and GPU 3. So you can use CUDA colon 1. So this will bring the data to the GPU 1 or the second GPU basically. X.device will show exactly where it stays, where the data is currently. Torch.device will actually see if we have the CUDA or we use CPU. So sometimes you will see that torch.CUDA is available, else CPU, right? So this is the line of code that you see usually. So that will actually check whether we have GPU system or GPU device. We can use that, or else we will use CPU as the default target of the data. Shape, stride and contiguity of the data will be managed by these functions like shape, size, ndim, numel, then dtype. So all these functions are being run in the handout that I will show. The essential tensor operations are the addition, multiplication, subtraction, element wise we can do. We can also do broadcast if shapes differ. Okay, so that also we'll see in the handout what exactly this broadcast means. We can do matrix multiplication where x at y, or tosh.matmul xy will do the matrix multiplication where x and y are matrices. We can operate on this, so element wise operation. We can check the maximum, minimum, the mean value of the tensor that is filled with the number of or collection of data. Similarly, we can use the reduce along the specification dimension by using dim equal to 0. So, which dimension I want to reduce. So, how this reduction happens, that also we will see in the handout. Again, the reshaping will be also done by several methods, like view is there, reshape is there, unsqueeze, squeeze, permute, right. So, all these operations that we will see in the handout. Indexing and slicing is also done by the exact method that is applied on the array elements in the NumPy. So, if you have used NumPy, the similar slicing and the indexing is allowed. Like x0 will actually access the first row, x minus 1 will be accessing the last row, x1 2 3, this colon is the slice. So, 1 2 3 will access from the first row to till the second row, and then the x greater than 0 will boolean mask the elements that is satisfying this condition. And similarly, this is also another way to slice all rows first column like NumPy, right. So, this is another way to slice the tensor. So, I will highly recommend to apply each of these notion of indexing, slicing, reshaping and the tensor operations, and also try to see what are the shapes and size or stride that you are getting after different operations for the tensors. Here is one such example, like let us say I have x dot view 2 minus 1. So, I am reshaping this 2 3 4 dimensions. So, basically I have 3 by 4 matrix and two such channels are there. So, here I can define this image as this 3-dimensional tensor, right. So, if I have 3 instead of 2 here, so I can have 3 channels, RGB channels, which has each channel size of 3 by 4. So, this is one way of seeing the size or the tensors in the visualized manner. Okay. So, here we have 2 by 3 by 4. So, each 2 3 by 4 channel representing here, and if I want to reshape it to 2, so essentially 2 rows will be there and all the rest of the dimension will be merged into columns. So, you can see that 3 by 4 is merged by 12. So, 1 to 12 is the number of columns that we get with 2 rows. So, 2 we are keeping it as same, and merging, so minus 1 is basically merging all the elements in this dimension. So, minus 1 infers the missing size view shares data when the layout is compatible. So, essentially we get the 212 instead of 2 by 3 by 4, we are getting 2 by 12. Similarly, reshape 2 by minus 1. So, here we are reshaping. So, reshaping and view is almost similar. View is equal to reinterpret the storage. So, here the storage, how we are storing the data, and reshaping is basically a view if possible, otherwise it will just copy the entire data into this reshaped architecture or reshaped manner. Unsqueeze, x dot unsqueeze is basically to induce a new dimension. So, it's as the name suggests, unsqueeze, that means it will add the new axis. So, here you can see that one new axis is added. So, 3 by 4 this matrix is now 1 by 3 by 4. Now, here you can have squeeze operation also, which will do the reverse operation, which is basically squeezing this first dimension, let us say 3 by 1 by 4. So, squeezing means it will squeeze to 3 by 4, removes all dimension whose size is 1 here. Okay. In practice, we will see how it works. So, permute also we can do. So, if we have, let us say, h by w by c, so channel height, width and number of channels. So, all are merged here, and you can see the red, green, blue channel in the image here, and the data is basically copied into all the channels. So, 1 is present in all the channel, red, green, blue, 2 is present in all the channel in this particular dimension or in this particular place. So, the permute will use this based on what exactly we want to permute. 201 is permuting to bringing the second to the first. So basically 0, 1, 2 was my dimension in the previous before conversion. After conversion, the 2 will come in the 0th place, 0 will come in the 1th place, because here 0 is present here. You can see these zeros position here, right? So 0 position is 0's position, 0 in the previous dimension is present here in this position after permute. So H will come in this place, C will come my first place, so 2 will come in the first place, and basically W will go into the last place. So then by this computation or this permutation of HCW is becoming CHW, where we have the channels first, and then H by W tensors are there. So my C means how many such channels will be there. So this is how we are reshaping or permuting the tensors. So all these permutations are also applicable, or any dimension of tensors that you can think of. So that's why the handout that we will be providing you should also play with the different dimensions and actually see how it actually transforms or the converts the different shapes and sizes into new dimension of the tensors. Broadcasting is one important operation that we usually use in the PyTorch, because PyTorch handles differently shaped tensors, and it might be confusing at times if you do not know exactly what broadcast means, because sometimes you will see that the tensors are not matching, the dimensions are not matching, but the operations that are happening in practice is valid, okay, and sometimes they are not valid. So based on what exactly is allowable and what is not allowed, so based on the different dimension computation, the broadcasting is one such example where this handling of differently shaped tensors can happen, and essentially that will define or that will initialize the new shape of the tensor. So here you can see A is one such tensor of shape 3 by 4, but B is a tensor with shape 4, right. So here we have 1 by 4 will be treated as, and when we perform this operation C equal to A plus B, basically B will be broadcasted over all the rows. So essentially it will be a valid computation, and you will see in practice how it happens. So broadcasting means it can broadcast values, or it can copy the value across the rows or across these columns based on what dimension that we are trying to broadcast for. So here we have the shape of A 3 by 4, here we have 4, and we are getting C as 3 by 4, where this 4 means what? 4 elements, right. So 3 by 4 means what? 3 by 4 means 3 rows and 4 columns, right. So essentially when we broadcast this row, that means 4 element, that means it will be broadcasted as each row, that 3 by 4 will be the new shape of this B after the broadcast, which will be added element wise here and generate the C tensor here, target tensor, and that will be valid operation because we can broadcast the 4 values from the column side to 3 rows. So so that way it will happen. Similarly we can have row broadcasting, you can have column broadcasting, and so on and so forth. So per channel broadcasting also you can have. So based on what exactly the dimension that you are playing with, like adding 4 is allowable, but adding 3 will not be allowed, because you have the 4 column elements, right. You cannot broadcast into 3, so then you have to have this column broadcast. So 3 should come to the column side, so that you can do the column broadcast, so that all the rows, 3 element of rows will be broadcasted into all 4 columns, right. So that way it should work. So again in the handout you will be getting these in broader sense, and you can have the aggregation reduction operation, like sum will do a scalar computation for all the elements. It will do dimension wise, so sum over all the rows, sum over all the columns based on the dimension that we are applying for. We can do the mean operation, we can do max operation, again dimension is also applied here, okay. In place operations are also useful at times. In place operations are defined by operation and underscore followed by that. So here add underscore is an in place operation. That means x dot add underscore y means x equal to x plus y basically. Okay. So that means in place will be replacing the original matrix or the tensor to its resultant value. Okay. So we need to apply it carefully, because if we are doing the gradient computation, in the gradient computation, if we want to use this type of in place operation, if we change the value or the matrix or the tensor itself, then we will not get exactly the gradient correct values. Okay. So rule is never use in place on tensors that are participating in the autograd graph. What exactly autograd graph, that we will see in the next. Similarly, the NumPy interop operations are also applicable. So we can use the conversion from NumPy array to torch, torch to torch tensor to NumPy array, and so on and so forth. Autograd or automatic differentiation is the core or the heart of any tensor that we are defining so far. Okay, because inputs are the data. So data are defined by the tensors. Their data type is defined by the different data type or D type that we have seen, but essentially these are used as the computation flow or computation graph. So computation graph means, let's say I have one operation y equal to w into x plus y w square. So where w is a tensor of 2, let's say this is a tensor of 2 value initialized with, so this is a scalar tensor, and x is also 3. Okay, and you can see that y is the output here, and to get this output we have the input as x as well as w. Now in the beginning we have said that we need to know exactly the leaf tensor and the non-leaf tensors. So which inputs are actually contributing to the computation of the gradient of the entire let's say output. So what is exactly the EI workflow? So EI is basically any neural network algorithm which is computing the loss in the end, and we are trying to minimize the loss. Loss is basically a scalar value, and we want to minimize the loss for which the weights are or parameters are reducing the loss function. Okay, we want to find that particular sweet spot or combination of weights or parameters. So for that, what we do the gradient computation, for which change in the weights or parameters will lead to the reduction of the loss function, right? So that is exactly what we do, how we train the model, right? So we want to reduce the loss function by changing the weight values. How we change? We compute the gradients with respect to the loss function or loss value for each of the, with respect to each of these weights and biases, and we try to update based on the gradients, right? So to compute these gradients, we need to exactly know which are the weights and which are the parameters, right, which are contributing to, or which are basically the parameters which are contributing to reduction in this loss. So some inputs can be constants, some inputs can be parameters. How to define them? We can define them by requires grad equal to true or not. Requires grad means what? We are trying to compute the gradient of the loss function with respect to this input. So that is called the requires grad true or false. If they are constants, we do not need to take care of these gradient computation because they are constants. If we are talking about the parameters, we need to have the gradient computation with respect to them for the loss function, right? So let's say if we have loss as L, so del L del W, right? So you have seen in the neural network training. We will not go into the details of defining the training, but this is just the revision of the training or how inputs matter in the training phase. So how input matters the training phase? So W is the set of parameters, let's say. It can be scalar, it can be tensor also, I mean collection of or multidimensional tensor. So here W is essentially your input, X is also input, but this is your leaf tensor and this is non-leaf tensor, because this is required grads true and this is just input which is not tracked, because I do not need to track the gradient for this input because this is just a constant input. Let us imagine that L is the loss here. So, where we are computing this y dot sum is the sum of all the elements in the tensor. So, here we have the y as scalar, because y is w into x, w is also scalar, x is also scalar, but these are usual, or these are the standard methods that are applied into the neural network training. L dot backward, this computes the delta or derivative of the loss function with respect to the w. So, that is why we needed to have this requires grad equal to true here, and this is automatically done by the autograd method in the PyTorch. What it does? So, it creates this computational graph. So, based on that, let us say I am computing this w as log of x into y. So, x into y, x and y is the input here. This is going through this multiplication operation and v is computed. This is the output of this multiplication operation. This is input to the log function here, and which is giving the output as w. So, this is the computational graph, the flow of input to the output. Now, here all these are tensors, x tensor, y tensor, v tensor, w tensor, and so on and so forth. Maybe now here x and y is tensor, let us say input tensor, and for which I want to calculate the gradient for, right. If my x is parameter, then I will compute this gradient of w, or the output of this loss with respect to x, right. So, we need to actually backtrack through which operations that it came or it traversed the input till the output, so that we can apply the calculus chain rule, because you know that we are usually using chain rule to compute the gradient of the loss function with respect to all the inputs, and that is why you need to track all the operation derivative. And that is why when these computational graphs are defined in parallel, the PyTorch Autograd machine, what it does is that it creates this derivative of the backward functions in parallel, and so that when we do the backward function, it creates, or it multiplies all the partial derivatives that are running through these derivative function or function derivatives. You can go to this PyTorch blog to understand the PyTorch Autograd engine, how it works, but it essentially computes this gradient of loss function with respect to the weights automatically, right. We saw the computational graph, we saw how it works, and whether we want the operation or the tensor which are going from input to the output or traversing through these different operations, we want to track their gradient or not, that will be defined by the true or false that we have seen, right. By default, the requires grad true is usually false if we do not define explicitly. So, for y we are not, for x we are defining here as explicit true, for w also we are defining here explicit true. That means, for both of them we are trying to track the gradient for, okay. We can detach the gradient tracking for tensor level. So, we can use this decorator function like with torch dot no grad y equal to model x. So, this will not track any gradient. So, this will do only the forward pass, and that will gradient will not be tracked. So, this type of method is usually applied for inference time or evaluation time. I do not want to calculate the gradient. So, the autograd engine will not automatically start the parallel let us say gradient function computation all on top of the computation graph. We can use the retain graph equal to true to by default graph is freed after the backward pass, backward method that we have seen, right. So, when we do the backward method call, the gradient will be computed, right. So, if we set the retain graph equal to true, then the graph is freed by default, but it will retain the graph, the computational graph, and it keeps the graph in memory. It will be expensive because it will create the memory for keeping all these gradient values in memory, but it will be useful for multi-loss training, because when we do the multi-loss training, the same graph, let's say we will run the two losses, right, or computation on two losses using the same graph we want. So basically it will not create new graphs, and the same graph will be applied to two new losses or multi losses. Higher order gradients, so computing gradients of gradients, higher order gradients computation also will be facilitated by return graph equal to true. If y is not a scalar, must pass a gradient argument, because y dot backward, if this is not a scalar, so torch dot once like y, so this must pass the gradient argument. So these type of cases will make sure that the gradient is computed, right, and by default the product of gradient vector Jacobian product will be computed. So always reduce your loss to scalar before calling backward, because we usually run the loss function as scalar and then we try to backtrack the or use the backward method to track the autograd engine through the different layers of multigrad computation, and basically we compute the gradient of the loss function or loss value with respect to each of the parameters that is being used in my model. So in summary, the tensors are n-dimensional arrays. You can have any dimension, any shape, any device they can use. Requires grad equal to true. By default it is false, and it usually uses the track operation. If it is true, it will track the gradients, and if it is false, it will not track. So it will call a backward function to compute these gradient values, and no grad will disable the graph building the during inference. We do not need to compute the grad or gradient computation, so that time we do not need the grad. However, this optimizer dot zero grad must be called. So when we will do the full training and we will see how to apply this gradient or autograd engine, we will see that in each step we need to make sure that the gradients are 0, otherwise it will accumulate in each step basically. In the handout also we will see the same. PyTorch uses dynamic computational graph. We will see the dynamic computational graph in the handout also, which is basically built in fresh in each forward pass, basically based on any conditional that is happening. If we want to apply any conditionals on the graph computation, so then we will use these. Usually these PyTorch dynamic graph helps us to do that. We were talking about these handouts. So handouts will be given to you as the week 4 handout, and in this handout you will see these experiments with the different shapes, sizes, the data types. You will see the experiments with the different operations, arithmetics, the multiplication, reduction, the reshaping, sizing, slicing, indexing, and so on and so forth. Also several broadcasting and their rules that is applicable for that. You will see the outputs and the different shapes, and you should also play with the different shapes while you are running these tensor methods. Also we will see the autograd, building the computational graph, how the gradients are computed, how their shapes are there. So in detail we will see in the training also how these shapes and sizes does matter in the autograd computation, and also no grad, detach, and the retain graph, how these are applicable. So all these are given to you as a handout, and you should practice with varying sizes of tensors as well as different tensors you should use and change the values and see how it varies. So in the next segment we will see the entire training workflow using these the tensor methods that we have seen in the segment 1. Thank you.